Welcome back, class. So let's talk more about benzene. August Hückel proposed that benzene alternated their double bond, single bond via equilibrium process. So you can see there that the double bonds, they shift around, and it's due to just equilibrium. Now, if that was the case, if I draw benzene here, not right there, let's go right here. If I draw benzene, okay, if this was an equilibrium process, what we would observe is that a single bond would have a length of 154 picometers, and a double bond would have a bond length of 134 picometers. Okay. But guess what? That's not what we observe. What we observe is that the bond length between these two carbons and the bond length between these two carbons is exactly the same. They're both 139 picometers. That's crazy to think, because we have learned in other classes that when you compare a bond between a carbon-carbon single bond versus a carbon-carbon double bond, that the carbon-carbon double bond is going to be shorter than the single bond. But when we go and take our measuring tapes and measure these bond lengths of benzene, they're exactly the same, which is kind of crazy to think about. Now, why would they be exactly the same? How many of you guys love resonance structures? How many of you don't? But resonance structures helps us to understand what's going on. And so, in actuality, what's going on is that because you can have a resonance structure where these pi electrons go there, and then you have this resonance structure. All right, like that. You have those two resonance structures, and it's due to resonance, okay? Remember that resonance, I like to give this analogy, okay? So this is a cool thing about resonance. Okay. So does anyone know how to breed a mule? Okay. Well, it takes two animals. You need a horse and a donkey. Right. When a horse and a donkey breed, you make a mule. But now let's just add a little bit to, let's say we have a blue horse and a red donkey, and that's going to make us a purple mule. Okay. Now, when these two animals breed to make a mule, and we have a purple mule, does that purple mule go, one day it's a donkey, and then one day it switches back to a mule, and then it switches to a horse, and back and forth? We know that's not possible, right? The mule is a mule. And in our little analogy, it's a purple mule. It does not go back and forth between these two species. The same thing with resonance structures. Benzene is not going from this form to this form, back, forth. That's not what it is. It is just benzene. And the best way to represent benzene as it actually is, we could say there's a double bond here between these two carbons, but then it's a single bond over here. So you can just represent that by the dotted lines. And now when you look at it that way, you can see that the bond lengths are going to be all the same. Whereas here you might fall in the trap like, ooh, double bond character is going to be shorter than a single bond. That's not what's going on. It looks like this. And so in order to draw benzene a little bit easier, we use the Hückel structure where we just put a circle like that. So this is benzene, and this represents that, and that, and that. So you will see from now on, I'm going to draw benzene with just the circle in the middle because it's so much easier and quicker to do. Now we have aromatic stability here. Not every cyclic compound that has alternating double single bonds is going to be aromatic. So that cyclobutadiene molecule you see on the PowerPoint, that is anti-aromatic. How do you know? Well, I'm going to teach you the rules. When you look at a molecule, you can determine if a molecule is going to be aromatic or anti-aromatic. Okay, I'm going to show you those tricks. But what this slide is trying to show you in that second image is you see that molecule with the 8 carbons. You can see that you have double, single, double, single. It's all conjugated, right? So you would expect it to be aromatic. And if it was aromatic, it would not react with the bromine, because remember when we did benzene with the elemental bromine, there was no reaction because benzene's aromatic, right? But when you do it with that 8 carbon species shown in the PowerPoint slide, it does react. So that evidence kind of suggests that maybe that molecule is not aromatic. So how can we figure it out? Okay? So that's what we're going to do in this slide right here. Now, in order to do this, okay, let's get us some more board space here. So let's review benzene so we can compare and contrast. Okay? So here's our benzene. Now, is it aromatic? We got to go through the 4 rules. Is it cyclic? Yes, it is. Are all the carbons sp2 hybridized? And if they're sp2 hybridized, then it means that they're planar. So Hückel's rule says it has to be planar. Rule 3 is conjugated p orbitals. And then 4, it has to satisfy the 4n plus 2 equation. Now those 4 rules are called the Hückel's rule. And I kind of just said that without actually explaining that. So what we have is what's called the Hückel's rule. Okay. Hückel's rules are 1 through 4. And those explain if it's aromatic. Now I want to double check and make sure we understand that we can see 1, cyclic, check. All carbons, sp2 hybridized, check. Conjugated pi system, what does that actually mean? We see a double, single mode right there, and that's a conjugated molecule. Now we have to count how many pi electrons are in the ring. And so you're just counting how many double bonds there are, and there's 2 electrons per double bond. So 2, 4, 6. There's 6 electrons. Now, can I find an integer, a whole number integer that makes this equation true? And if I take n equals 1 and plug it in here, 4 times 1 is 4, plus 2 is, in fact, 6. So 6 does equal 6. And so that satisfies the Hückel's rule, making benzene aromatic. Now let's compare that to cyclobutadiene. Okay, and take a look at that. Is that aromatic? Well, we got to go through the rules with every one. Is it cyclic? Yes, it is. It's a ring. When you look at the carbons, are they sp2 hybridized? And they are. So they're sp2, so that molecule's flat. Are there conjugated pi orbitals or conjugated p orbitals? Yes. Each of those carbons are sp2 hybridized. And if carbons are sp2 hybridized, remember the hybridization state? There's sp2, and then there's that p orbital right there. So those are all sp2 hybridized, so they all have to have a p orbital, and they're all conjugated. All right. And then step 4. 4n plus 2 equals, how many pi electrons do we have in cyclobutadiene? There's 1, 2, 3, 4. Now, is there an integer to make this statement true? If I put in 0, 4 times 0 is 0 plus 2 is 2. 2 does not equal 4. So let's try a different one. What if I put in a 1? 4 times 1 is 4, plus 2 is 6. 6 does not equal 4. And so, well, if you try 2, then you just see it's just getting bigger and bigger, and it's never going to be true. 4 times 2 is 8, plus 2 is 10. 10 doesn't equal 4. So this molecule, K, is definitely not aromatic because it doesn't satisfy this equation right here. So is the cyclobutadiene non-aromatic or anti-aromatic? If it's anti-aromatic, there's a new equation. 4n equals the number of pi electrons. All right. So if we take that equation now and look at it again, how many pi electrons are there? There's a total of 4. Now, can you plug into n, a whole number integer, that makes that statement true? If you put in a 0, that doesn't make it true. But what if you put in a 1? 4 times 1 is 4, which equals 4. And so this molecule right here is anti-aromatic because it follows this equation right there. Okay. Now what's interesting about cyclobutadiene, okay, erase this here. Is when you take a look at cyclobutadiene and looking at it that way, and we're thinking in terms of resonance. What's interesting, this is so cool, is when you go and take your measuring tape and figure out the bond lengths, what you would expect based off of what I previously taught you, you would expect the bond lengths to be exactly the same. But that's not what we observe. And then that bond length is 160. The bond lengths are different. They're totally different. So if they're different, then that means there's no resonance. There's no resonance in this cyclobutadiene. It's anti-aromatic. It's very, very unstable. Anti-aromatic compounds, very unstable, and cyclobutadiene is so unstable it only forms in the gas phase, and it's just like for very small amounts of time. Okay, so when we take a look at this slide here, let's make it a little bit larger so we can see it. The MO can help us understand a little bit more as to why this is anti-aromatic. And it all has to come down to, when you look at that MO diagram, the image on the right, do you see how there are pi electrons, 2 of them, in the bonding molecular orbital? But then you have 1 electron in 2 non-bonding orbitals. Okay. So what that's trying to show us here is that we have 2 electrons that aren't even in bonding orbitals. They're not forming any bonds, they're just there. So whenever you have an aromatic compound, you're going to have the electrons in the bonding orbitals. But the moment that you start introducing electrons into non-bonding orbitals and anti-bonding orbitals, the odds are your compound's going to be anti-aromatic. Okay. So let's look at a few other examples of compounds. Okay. So cyclooctatetraene, that's a mouthful. When you look at that molecule, you see that there are 8 carbons. You see that it's double, single, it's conjugated. So if we go through the Hückel's rule, number 1, is it cyclic? Yes, it is. Clearly, it's in a ring. Number 2, are all the carbons sp2 hybridized? Yes, it is. So you would assume that it's planar because every single carbon is sp2 hybridized. Do we have a conjugated p orbitals? You can see that with the image there at the top with the red and blue orbitals. You can see the p orbitals are all conjugated. And you can see it in the skeletal structure where it's double, single. Now when you do the, let's go right here, 4n plus 2, how many pi electrons are in this molecule? There's 1, 2, 3, 4, so there's going to be 8. So if this is true, then that compound's going to be aromatic. But you will see that there is no integer that you could plug in here to make the statement true. So it's not aromatic, but if you go 4n equals 8, you can find an integer to make that true. And so 4 times 2 equals 8. So this compound is based off of the 4 Hückel's rules that we've outlined. This molecule should be anti-aromatic. Okay? But here's one of the twists. Okay? This compound is, in fact, it is not anti-aromatic. But you might be thinking, Dr. Lawrence, we just went through all the rules and we proved that it's anti-aromatic. Well, look at what cyclooctatetraene does. It's not planar. it has more of a boat shape. Now, why would it do that? Why would the molecule be sp2 hybridized, so you would envision it to be flat, but then it does this boat shape, and now it's not planar? Well, the reason why this molecule does this is because being anti-aromatic is really, really high in energy and unstable. It's very, very uncomfortable for the molecule to be anti-aromatic. So if it can bend out of planarity and become a different shape that's not planar, it is now no longer going to be anti-aromatic. It is going to be non-aromatic, or just a normal molecule, non-aromatic. So that is an exception to what we have been seeing up to this point. Isn't that crazy? So you might be freaking out a little bit like, well, how do I know if a molecule is going to be planar or not? Because I found that in this example, all the carbons were sp2 hybridized. So why isn't it planar? So here's what I'm going to do for you. I'm going to have my own little rule for you to help you with this. Okay? If you come across a molecule that's less than or equal to 7 atoms, all right, it's always going to be planar. So on the test or any quizzes, if it's 7 or less atoms, and you see that the molecule is every atom is sp2 hybridized, it's going to be planar and flat. All right? But if it's going to be greater than 8 atoms, it's going to depend. Some molecules that are greater than 8 are aromatic. Some are anti-aromatic. Or let me put it this way. Some molecules that are greater than 8 atoms are going to be planar, and some are not. So how do you know? Well, you don't. I will have to tell you. So if the molecule is greater than 8 atoms, I will tell you if it's planar or not. Okay. Okay, the next topic that we want to work on is something called frost circles or frost diagrams. Frost diagrams are used to help you and me figure out the energy levels for the molecular orbitals. Because when we look at molecular orbitals, we can gain some information as to if the compound is aromatic or anti-aromatic. So we need to be able to draw our MO diagrams, and frost circles helps us accomplish that. Okay? So when you look at the steps here, it tells you to draw a circle. Okay? So if we draw ourselves a circle right there. And then step 2 says you need to put in your molecule. So if I want to look at cyclobutadiene, I need to place that into the circle. But here's the kicker. Okay? You have to find a corner. Okay? And that corner has to be right in the middle at that point. And then you draw the molecule. Okay? You see, there's my cyclobutadiene. Now you don't have to put in the double bonds. Okay? Now, after you do that, every corner that's touching the circle is going to be a molecular orbital. So you could say, hey, there's a molecular orbital, there's one, and there's one. That's what's going on here. After you've decided that, that's now going to represent the energy level of those molecular orbitals. All right? you're going to take a dotted line and go right through the center of the circle. And doing that is going to tell us what type of molecular orbitals we have. Every molecular orbital below the dotted line is going to be a bonding molecular orbital. Everything that's right in the middle, right there, those are going to be non-bonding. Okay. I don't like this pen. Let's get a different one. And then all orbitals above are going to be anti-bonding. Okay. And then now you have a MO diagram, and the procedure in the book says now to erase the circle and whatnot. I personally don't like to do that. I just understand that these are molecular orbitals. And when I look at my cyclobutadiene, I see that there are 4 pi electrons. And so I put those pi electrons in. 1, 2, 3, 4. Okay. Or we could put that the same way as well. Doesn't really matter. So, but now I can see that there's 2 pi electrons in the bonding and then 2 in the non-bonding. Okay. So let's do another example of this with benzene. All right. So we draw ourselves our circle. Okay. Oh, I've lost. Let's do another one. Okay. Not a perfect circle, but you got to do the best that you can. Now let's draw in benzene. So with the benzene, you have to put a corner, it doesn't matter which one, you can pick one, and it has to go in the middle of the circle at that point. Okay? What you're going to see when we do that, we're going to go boom. Okay, so there's my hexane, or benzene. And every point is a molecular orbital. Okay. We take the circle and go right down the middle and draw a dotted line. Okay? So what that's telling us here is these 3 right here are bonding orbitals, or molecular orbitals. And these 3 up here are anti-bonding. And you can't see that, can you? Anti-bonding orbitals. There are no molecular orbitals in the center of the circle, and orbitals in the center of the circle are going to be non-bonding. So in this example, we see that we have 6 pi electrons, so 1, 2, 3, 4, 5, 6. You can see all 6 pi electrons are in the bonding orbitals, and that is really, really good and very stabilizing. Okay. So one thing that you can see when you go through a few examples of Frost diagrams here, that it helps to explain why the 4n plus 2 rule in Hückel's rules gives us aromatic compounds. You can see in every single one of those, the bonding orbitals are always going to be odd. You see in the first one with the square in the circle, you have 1 bonding orbital. And then with the 5 carbon ring, you see 3. And they're always odd. Okay? And that helps us, that explains why the 4n plus 2 rule works. There's another way to name molecules or refer to molecules, and they are called annulenes. And you can see 3 examples right there. And annulenes are simply just counting how many carbons there are. So benzene, there's 6 carbons, so we could call it a 6 annulene, or 10 to 14. Okay? Now these compounds are getting much larger than 7 carbons. So these can as well be aromatic, non-aromatic, or anti-aromatic. It is all possible. So I want to show you a few of them and give you some more experience looking at these compounds. Okay? So the 10 annulene, okay, we see that it's cyclic. We see all of the carbons are sp2 hybridized. We see it's conjugated. But it is not going to be anti-aromatic or aromatic because it's not planar. If it was planar, do you see the 2 hydrogens in the middle of the 10 annulene? You see the steric clash? The steric clash is too great if the molecule is planar. So the molecule's like, can't do this. Too high in energy, so it bends out of plane, so the steric strain can be released. And now when it bends out of plane, it's no longer planar, so it's not going to fall into the categories or the rules of Hückel's rules. So that would be a non-aromatic compound because it's not flat. 14 annulene, you can see that there are hydrogens in the middle of the molecule. There's a little bit of steric clash. The molecule isn't perfectly flat, but it is mostly flat. And it's mostly flat due to that steric strain. But that steric strain isn't, it's a mild steric strain. And so 14 annulene is aromatic because it follows all the Hückel's rules, and we're bending the rules a little bit when we're talking about if it's planar or not. It's mostly planar. Okay. And then when you look at the 18 annulene, is that aromatic or anti-aromatic? Well, in this one, it is aromatic. So when you go through the Hückel's rules for the 18 annulene, you'd be like, is it cyclic? Check. What's number 2? Is it sp2 hybridized? Is it flat? Well, I'm going to have to tell you it's flat because it's greater than 8. Yep. Is it conjugated? Yep. And does it satisfy the 4n plus 2 rule? Does it? Let's give it a try. 4n plus 2 equals, how many electrons are in 18 annulene? Count how many double bonds there are. 1, 2, 3, 4, 5, 6, 7, 8, 9. Did I do that right? Let me try it again. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 times 2 is 18 electrons. 18 pi electrons, right? So do we have a statement to make that true? So 4 times, let's say 4. 4 times 4 is 16, plus 2 does in fact equal 18. So that 18 annulene is going to be aromatic because I told you that it's planar. Right. Okay, what time do we have here? Okay, we still have some time. Now we have some compounds that can be aromatic when they are anions or cations. That's interesting. So let's take a look at that. Let's take a look at a compound that's called, let me write it out first. That's one squeaky pen. Let me get rid of that slide. So we can see it a little bit better. Okay. So we have the cyclopentadienyl anion. All right. And what does that look like? It looks like this. Has a lone pair with a formal charge of -1. Now we want to know if this compound is aromatic or not. Well, we just got to go through the Hückel's rules. Is it cyclic? Yes. Is it planar? Are they sp2 hybridized? All right. So we can see here when we look at these carbons right here, we see that there is 1 electron group, 2, 3. There's 3 electron groups. So those carbons right here are sp2 hybridized. All right? But when you take a look at this carbon right here, how many electron groups are there? When we count them, you can see that there's the lone pair, that's one group. That bond is a group. I count 4 electron groups. And so you might be tempted to say, hey, that's sp3 hybridized. But you gotta be careful. If the lone pair is involved in resonance, so let's take a look at it this way. All right, so let me redraw the molecule. If the lone pair is involved in resonance, no, that's not what I want to do. Can't do that. I'm going to bring that lone pair and bring it there. Now when you look at that carbon, right here, do you see now how it has 3 electron groups? So now that looks like it's sp2 hybridized, does it not? So over here it looks like it's sp3, and over here it looks like it's sp2. So what is it? Well, when you have something like this, you're always going to pick the lower of the hybridization states. So if it's sp3 in one resonance structure and sp2 in another, it's actually both of these carbons are in fact sp2. Both of them are sp2. All right. So that means that every single carbon in this anion is sp2 hybridized. So it is planar. And it's less than 7 carbons. So you just, off my rule, it's going to be planar. 3, okay. Is it conjugated with p orbitals? Well, those electrons right there are in p orbitals. So what do we, if this carbon is in fact sp2 hybridized, it has a p orbital. So we've established that every single carbon here is sp2 hybridized, so every single carbon has a p orbital, and it's conjugated. Okay. If we want to draw it, we could get rid of this hydrogen to make it look easier. We could say, hey, p, p, to see how there's p orbitals all conjugated. Okay. And then does it follow the fourth rule? Put it down here. 4n plus 2. How many pi electrons are in this molecule? Previous examples, I told you to count how many electrons are in the double bonds. That there's 1, 2, 3, 4. But if the lone pair is involved in resonance, you have to count that lone pair as well. So what we have is 2, 4, 5, 6. And the reason why I'm counting these two electrons, the simple answer is because those are in p orbitals. I'm counting all the electrons in p orbitals. So the trick is, if the lone pair is involved in resonance, it's in a p orbital. So we count them. So 2, 4, 5, 6. And we know 4n plus 2, there is an integer that makes that true. So cyclopentadienyl anion is in fact aromatic. It satisfies the 4 Hückel rules. Now there's another molecule that is a cation that is aromatic. This one's not rubbing off, so I'm going to pause the video for a second. Now, before we get into the cation, we have this slide here that shows us why the cyclopentadiene is kind of acidic. And the reason why that molecule is acidic is because when the acidic proton is ripped off by the base, and in this case the hydroxide, you can see that what do you form? You form an aromatic conjugate base. And we have learned in previous chapters that if the conjugate base, which is the anion in this case, if that conjugate base is very stable, then the molecules are going to be acidic. Okay. So cyclopentadiene is relatively acidic because its conjugate base is going to be an aromatic anion. So that's pretty cool. So let's take a look at this cation. This cation is aromatic, and this is a fun example right here. So it's 7 carbons. So we already know from the start that it's going to be flat based off of Hückel's rules and my little minor rule. If it's 7 or less, and it follows the first 2 rules, or the first rule, is it cyclic? When we look at that cation, it is cyclic. Now, this tryptophan cation, okay, let's take a look at this. Let's go through the rules. Is it cyclic? Yes. Are all the carbons sp2 hybridized? And when you look at that, right, you can see that the carbons with double bonds are sp2 hybridized. But what about, I'm going to draw part of the molecule. What about the cation? What is the hybridization state of a cation? Well, let's draw the cation. If it's positively charged with the formal charge of a positive charge, we know that there are 3 groups attached. So 1, 2, 3. If there's 3 groups, it's sp2 hybridized. So the tropylium cation, every single carbon is sp2 hybridized. Okay. So yes, so it is planar. Right. Step 3, every single carbon has a conjugated p orbitals. And so, is it conjugated? P orbitals? Yes, it does. Every carbon has one. So that right there kind of gets a little tricky because you look at that, because previously when we looked at benzene, we see it's conjugated because it alternates double, single, right? But with the tropylium cation, you do have that segment where it is a single, okay? But the real definition is p orbitals, okay? Because each one of those carbons right there has p orbitals, okay? So don't let that one trip you up, okay? And then it does, in fact, satisfy that rule. Because how many pi electrons are in the tropylium cation? There's 3 double bonds, so that means that there's 6 electrons. So 4n plus 2 equals 6 pi electrons. Isn't that cool? The next area that we need to spend some time in is aromatic heterocycles. And so we are going to talk about pyridine and pyrrole, and both are aromatic, but what gets introduced in this next section here we only have a few minutes left here, so I just want to take the time to introduce this. When you look at pyridine, okay, versus pyrrole, they're both aromatic, but the question that arises is you have to realize that there's lone pairs, okay? And if we use the 4n plus 2 rule, you can see in pyridine here, if I only count the pi electrons with the double bond, so 2, 4, 6, that's going to give me an aromatic compound. But if I choose to count the lone pair on the nitrogen as well, it now becomes anti-aromatic. So let's do that same analysis with the pyrrole. If I only count the double bonds, that's 4 electrons, so that would make it anti-aromatic. But if I count the 4 in here and the lone pair, I have 6. And now pyrrole is aromatic. So it raises the question, when you have heterocycles with lone pairs, when do you count the lone pairs and when do you not count the lone pairs? And that's what the next video is going to discuss in detail. Okay?